Yeah. That's good. It's a trans. Yep. Very good. That's good. It's so really I'm so that. Let's see. I can I finish. You want to take slides? Brought my own chalk. See if that helps. Make sure. Okay. Really? Oh, my days. Okay. So today's class, I'm going to finish up. Hopefully, we'll see how far we get. Obviously, remember, you can always stop and ask me questions at any time. But yeah, we'll cover a few things such as the reversible logic gates, error correction, Turing machines and complexity class, and the church Turing thesis. All of this will be at a somewhat high level. We'll go into some details, a couple of things, but most of that will be at a high level because that's not really the focus of this course. But you should have some working knowledge of these terms so you can understand what we are talking about later on. Okay, so we discussed how logic gates could be made into electric circuits. And as you may recall, we showed, for example, a simple operation like addition of 2 bits. The sum and carry can be executed as a logic gate, as 2 logic gates, XOR and AND. And I did make one small mistake in the last class, which was that when I talked about Shannon's theorem, remember about that there are universal logic gate sets. I said that any function can be converted to any binary function converts binary strings to something else can be efficiently written, and that's not true. So it can be written, but it may not always be efficient. So that's an important point because actually, if everything could be efficiently written that way, I would have proven that P equals NP, which is not true. So anyway, or he would have proven that, not me. Okay, and we discussed the different types of universal gate sets. And so now today I want to introduce a new, by the way, any questions about any of that from last class? Okay, if not, let's talk about reversible gates. So far, a reversible gate, as the definition implies, is where given the output, we can tell what the input must have been. Okay, and so a NOT gate, for example, is reversible, and we can know that if, for example, by simply taking the output of the NOT gate, we wire it to the input of another NOT gate, it'll give us back the original inputs. And so for every operation, if there exists some gate circuit that we can use to undo the operation, then we say that that gate is reversible. But there are several operations in the universal gate set that I introduced that are non-reversible or irreversible. And the obvious reason for that is, for example, AND, it takes 2 inputs, A and B, produces only 1 out. right? The A times B. Same with OR, same with NAND, same with NOR. So the number of outputs is lesser than the number of inputs, it's immediately irreversible because there are several combinations of inputs that give rise to the same output. So you may ask, why does this matter? Why do you think it might matter? Anyone? Yes. Yes.
Computers won't accidentally run in reverse.
Computers won't accidentally run in reverse. I hadn't thought of that. Let's say. Be important. Sure. I mean, maybe that's an additional reason. Yes.
Well, like along that support, like there is going to be an order in your circuitry. It has to go. If
So-
you're using like an AND gate, you have to have like you can have like the AND gate come before
Mhm.
an XOR gate, and it's not gonna like mix up the order of functions.
Yeah. Oh, I guess that's kind of what he was
Yeah.
trying to get to. Yeah. Okay. Yeah.
Encryption.
Encryption. Huh, I like all these interesting ideas. Honestly, I hadn't even thought of it. Yeah, go ahead.
It makes error checking more difficult because you can't just look at what you got and know where they occurred.
Yeah. Yeah, that's good. Yes, one of the reasons might be that. So, and the reason for that, in some sense, is loss of information, right? So, if we get some output at the moment, we can't tell which of many different inputs might have produced it. And so there's a loss of information, so to speak, which might be a problem. I don't necessarily say it is a problem, but I'm saying it might be a problem. And in fact, as it turns out, and one of the reasons we are interested in this is that so information loss, basically, is kind of one of the problems. And in the beginning of classical computing, people worried about it. Okay, and they came up with reversible gates. So there were two famous scientists, Fredkin and Toffoli. We'll introduce one of their constructions in a minute, but they came up with a whole theory of reversible classical computing, where you could run the operations back and forth. Okay, and of course we don't use it now. Okay, it was not very useful for development of computing. Although now that I think about it, maybe for all these other reasons that you all mentioned, maybe it should have been. So one of the things I should mention is I'm not a computer scientist, right? so you definitely, there's many other things I'll say today. You know, I am not an expert or authority on some of these things. So you should definitely be free to question or think for yourself about. I mean, you should feel free to think for yourself, no matter what, or question me no matter what, but at least I can say that I know more about some quantum stuff than I do about computer science stuff. So yeah, so I think that, but what I do know is Fredkin and Toffoli, they came up with this theory of reversible computing, which I'll introduce in a minute. But it also turns out that this is going to be very useful for quantum computing. So the idea that I introduce here, one or a couple of ideas, will turn out to be useful in quantum computing. And the reason for that, as you might have guessed, already we know from some of those experiments that I was talking about earlier, that if we lose a bit, if we measure a bit in quantum computers, then we have destroyed the superposition state, right? So losing information is not a good thing in a quantum computer. Okay, so let me introduce the first gate, which is a reversible AND gate. And this is called the Toffoli gate. So introduced by Toffoli. And his idea was, and this is a common theme in reversible computing, and will turn out to be very useful for quantum computing as well. So his idea was, if we just take the AND, A, B, and produce the AND of A and B, that's non-reversible. But if I introduce an extra bit, C, which I call the ancilla bit, auxiliary, ancilla, additional, whatever, different names for it, but C is an ancilla bit. And then we do an operation on C that will allow us to reconstruct all three, A, B, and C. Okay, and that operation here because it's an AND gate, is just A, B plus C, where plus here is modulo 2, which is XOR. Okay. And also notice I've allowed A and B themselves also to flow through to the end. So at the end, we also have A and B themselves. Now, in a quantum computer, this will turn out to be difficult because we'll come to that when we discuss quantum computers. But in a classical computer, it's easy to do this, right? We just take a wire and attach it to the input and bring it out to the output, for example. Well, there are more clever ways to do that or more power efficient ways that you have to do that, but you can do it in just that simple way, at least in principle. So here is the circuit, the digital logic circuit or the gate circuit for that, which is exactly what I just discussed. A, B is produced here, right? Which is what we want. And then we add that C and we XOR AB plus C. Okay, so let's work through this and make sure that it actually does what I claim it does in a minute. So, okay, this is just exactly what I said. And one other name for this is it's called the control not gate. And I'll explain why in a minute when we go through the truth table. Okay. But this conception is clear to everyone, what we have done. Oops. The truth table of the Toffoli gate. So let me work through the truth table here. See if the chart is short. We have A, B, C, and then A, B, XOR. Right? So we have 0, 0, 0, 0, 0, 1. 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, space. So that's all 8 possibilities. So A and B with XOR with C, that's still going to be 0, right? And by the way, we should keep track. Remember, the output has all 3 of these. So it has A, B, and then AB. We have 0, 0, 0. This is also 0, 0 plus 1. So this is 0, 0, 1, right? 0, 1 plus 0. Well, that's 0 times 1 is 0. And then plus the 0 again. So that's 0, 1, 0. And then 0, 1. So that XOR, the AND of those two is 0. Again, XOR now with 1. I preserve the 1, right? So then 1, 0. And now I again AND those, that's still a 0. XOR with 0, I get 0. And 1, 0 ANDed together again is a 0, but XOR with 1 is a 1. So now we've come to the final 2 rows. So 1 plus 1, 1 times 1, that's high, right? Because it's an AND. And then XOR with 0 is still 0. Oh, sorry, is 1. Right? Because 1 times 1 is 1, but then when I add it modulo 2 with 0, that's 1, obviously. And then the last one is 1 times 1 is 1. And when I do modulo 2 addition with 1, I get 0, right? So that's the final row. So what you need to notice here is that for every row here where A and B are the same, right? So if you have 0, 0, and then there is a row here that is different. So I can always return and figure out what the inputs were. Okay, so if I have 0, 1, or equivalently, I can like work backwards if I. All right, so the idea is that I always have a way to return back to the inputs from the outputs. Okay, they are unique in this case. All right. Unlike the AND. Okay. I'm kind of seeing this. That's just the same truth table. Now, and the other thing to notice is that the output has the values flipped, right? So it's always 0, 1, 0, 1, 0, 1, and the last one is 1, 0, right? So yeah, and the last point is, which is why this is called a control not, is that it will flip the output C when both A and B are 1. So it's controlled by 2 other bits. Okay. We will later on see in quantum computing something called a control not, where 1 bit controls whether another one is flipped or not. Okay, very simple idea, right? I mean, it's but this is just the same idea, but with 2 bits instead. Both A and B both have to be high, and then the output will be flipping C. Okay. Okay. So in general, there are many kinds of reversible gates. Here's for any gate with operating on 2 bits, A and B, and producing some output F of AB, which can be anything, OR, NAND, whatever. Then this construction works for that, for reversing that gate. Okay, the same construction. You just take another bit C, XOR the output of F, A, B with that, and then also give me the inputs A and B. Then this is the truth table. You can verify it fairly easily for yourself. And you end up knowing that you can always go from the output back to the input. Okay. Okay, so that was just a way to explain to you how reversible gates work. And at the moment, it's probably not clear to you why we need it, but except, as I said, we are preserving all the information. We're allowing time to flow both backwards and forwards in the circuit. Yes.
What's the purpose of doing that instead of just having like only the 2 inputs, just having A, B, and like if we're saying an AND gate, let's say, right? Why not just have A and B as outputs and then A and B as the third output? And then you still like, why do you need to have the C then?
So you should ask yourself if you can do that, right? Because remember, we need to be able to, so what operation are you going to run on the output of A and B to get back AB?
Well, if you like this one, you're taking out you're taking in A, B, and C and outputting A, B, then A and B XOR C.
Correct.
Why couldn't I just cut out the C as an input? And
and just have AB?
And A and B as an output. Then I have A and B individually and B.
You could do that, but then what you're ending up with is that you still will need like some knowledge of the truth table, I suppose. Right here, what I'm giving you is a way independent of the truth table. I'll always know what the inputs are.
Okay.
If you see what I mean.
Sure.
I can run the circuit backwards, so to speak, and I can get back the inputs. Yeah. Okay, so let's talk about errors now. So we talked about reversible gates. Let's now talk about errors. Because that always happens in every circuit, whether it's digital or analog. Now in digital circuits, as we talked about, some sources of error are reduced. For example, noise and distortion that are accompanying every electronic circuit. Some of them, those errors are not important, right? Because we can, to some degree, right? I mean, if the whole circuit blows up, that's a separate issue. But there are other ways in which errors can creep into circuits. So for example, it has been found that, a cosmic ray passing through a circuit can cause that bit to flip from 0 to 1, okay? Because it's a lot of energy and it's enough to like change the output of that circuit, for example. Same thing with radioactive particles. They're just another way. And there are radioactive particles all around us. I mean, they're in the soil, in the air, water, etc. And there's a well-known, situation where the water that was feeding some semiconductor plant had some radioactive stuff in it, and that ended up causing a lot of problems for the chips that are being made. And defects in the semiconductors also give rise to issues. So semiconductor crystal, we have made tremendous progress in very, very high quality semiconductors, and we know how to like create the defects the way we want. If you take a solid state physics class, you'll understand that semiconductors work because we can dope the semiconductor, that is, create defects in the semiconductor in a very controllable fashion. But sometimes there are other kinds of defects that occur in the crystal, maybe a broken lattice plane or something else, or some other defect that you didn't want to be there in the semiconductor. All of these can give rise to errors in the digital operation, okay? And of course, in communication, we are familiar with this problem as well, right? I mean, if I send a signal like a radio wave or a light wave, it gets absorbed in the atmosphere and it gets lost, right? So, and even on fibers, even though fibers are really good conductors of optical information, the photons do eventually get lost. Okay, so when I send a 0 over a noisy channel, I may end up with a 1, or I may send a 1 and it's lost in the transmission, and the receiver thinks no photon was sent, so it may say that it was a 0. Okay, and we overcome this typically in classical communication by several techniques. But as we'll see when we get to quantum, we can't use some of those techniques. But one thing we can do is we can transmit or encode the information in our circuits and in our communication platforms in such a way as to make them more resistant to the errors. Okay, so the simplest code that you could imagine is to call the repetition code. Okay, and the idea is very straightforward. You encode every 0 as 2 zeros, every 1 as 2 ones. Okay, so these two, which are our basis bits, if you like, 0 and 1, these have an even number of ones in the new code, right? Because this has 0 number of ones, which is even number, and this has 2 ones, which is an even number. Okay, this is the number of ones. The even number of ones is called even parity. Okay, not the physics parity, but this is just the parity in code words. If an error flips one bit, right? So it makes it, go to 0, 1, 0, 0 can go to 0, 1, or it can go to 1, 0. And similarly, 1, 1 can go to 1, 0 or 1, 1, or 0, 1, sorry, right? If only one of the bits can be flipped. So this 0, 1 or 1, 0, you can see they have an odd number of ones. Okay. And that's an odd parity system. Okay. So we can detect the errors. Okay. And how would you go about detecting the errors? I'll explain that in a second. But the strings 0, 0, 0, 1, 1, 0, 1, 1 are called the code words in this error detecting code or error detecting scheme. Okay. And we can use the parity measurement, which is measuring the number of ones in the string, to distinguish if an error has occurred. Okay. Such a measurement is called an error syndrome. Okay. So basically, it's just a fancy way of saying I make some measurement, some circuit, which will detect whether the error has occurred or not. And can we compute the parity with the circuit? Anybody have an idea how we could compute parity with a circuit here? So we need something that, if I go back, for zeros and ones, it gives me the same output, and 0, 1 and 1, 0 give another output. Yes, I see 2 hands. Anyone? Yeah.
XOR.
XOR. Very good. I don't know who said that, but yes. Excellent. Exactly. So you have an XOR gate, and then as you can see, 0, 1 XOR will give me 1, 1, 0 XOR will give me 1, but these two will both give me 0. Okay. So that is your parity checking circuit. But what about more than one error? Will this code allow me to correct for more than one error? So for example, if both bits got flipped, no, because 0, 0, if they both get flipped to 1, 1, that's a code word. and it'll therefore give me a, it'll say that's a safe code word, so we accept that, even though it's an error in the code. And also another question is, how do we fix the error? So it's all well and good to say, okay, I found the error, but how do I fix it? Do I know whether it was, a 0, 0 that got flipped to a 1, 0, or was it a 1, 1 that got flipped to a 1, 0? How do I know, right? I don't know in this scheme. Do you agree with that? Right? I don't know which of those gave me the number that I'm seeing. I would just have to throw it away and, ask the person to send it again or whatever. In the digital circuit, you can't even do that, right? You would just get an error in your computation, basically. Okay, so we now have error correction code, okay, where we not only can detect the error, but we can fix the error. Okay? So we use the 3-bit instead of 2. If 2 doesn't fix it, let's use 3. That's how clever we are. Okay. So now the repetition code with 3 bits is 0 going to 3 zeros, 1 going to 3 ones. And the code words for the single bit flips, right, you can easily work out. They are just these 001, 010, 100, 110, 101, and 011. And we can do error correction by taking the majority vote, right? So we say, if it's 001 or 010 or 100, they must all have come from flipping one of these, right? So I get a 000, I send that back to a 00. And 110, 101, or 011, they must have come from a 1-bit flip of the word 111. Okay. So that's easy enough in principle, taking the majority vote, right? How would you implement this? So we can implement the majority vote rule using, again, parity checks as the error syndrome. Okay. Now I'm starting to put together all these unfamiliar words. Hopefully it starts to make sense because we introduced them earlier. So the error syndrome is again parity, but now we're going to find the parity using all 3 digits. So we get 2 parity checks, right? So the 2 parity checks are very straightforward. So if I have written the code word as the bits B2, B1, B0, so that's most significant, then the first digit and the least significant bit, then the left parity bit is B2 plus B1, the right parity bit is B1 plus B0, modulo 2 XOR, okay? Okay, so the truth table of the parity checks is pretty straightforward again. Let's just do that very quickly. I could use this, but I'll try to write this in numerical order because I prefer writing the truth tables in numerical. Okay, was it in numerical order and I just screwed it up? Space. 3, 6. Oh, yeah, I don't know space. Sorry. Okay, I'm gonna have to read it. Okay. Here, we now have the 2 parity bits. There's the left parity bit and the right parity bit, right? So 0, 0, XOR that, 0, 0 XOR 1. 0 XOR 1, 1, 1 XOR 0 is 1. Yes, okay. 0, 1, 1, 0 XOR 1 is 1. Sure. Okay. And 1 XOR 1 is 1 XOR 1? Here, 0. Okay, 1 XOR 0, 1, 0 XOR 0, 1 XOR 0, 1, 0 XOR 1, 1, 1 XOR 1 is 0, 1 XOR 0 is 0. Okay. 1 XOR 1 is 0. 1 XOR 1 is 0. So we see that if I look at the two code words, remember our code words that transmit 0 and the code word that transmit 1, right? Those are these two over here. And those will have outputs 0, 0 with our parity check operator. Okay. So therefore, we know that if we get a 0, 0, we are definitely in the right, we have the right number, 0 or 1. Okay. And the other, if you can verify now easily for yourself, if I get a 0, 0, 1, right, then it's the left bit is 0, the right bit is 1. Okay. And if I get a 0, 1, 0, the left bit is 1, the right bit is 1, and 0, 1, 1 gives me 1, 0, 1, 0. So now we can start to implement majority rule. Okay. And the majority rule is just that if I get something like 1, 1, 0, which has this 0 and 0 with it, no, that must be wrong. 0. So yeah, so I'll know that one of the bits has flipped by looking at the right parity bit. So that's what I need to know. Right, exactly. So because I'm trying to figure out which bit to flip without having to know what the actual word was, right? And I can see that right here. Okay. So if I get a 0, 1 like this, right? I know that this bit must be wrong. The last one, right? So I flip that last one. And that's true even here as well. If I know that I got a 0, 1, I flip the last bit, I get back the right code word because this is the closest to 1, 1, 1. Okay. And if I get a 1, 0, then I know that the right bit must have been flipped. So I flip that one back to give me the right number. Okay. And if I get a 1, 1, then I know the middle bit must have been flipped. And I flip that one to give me the right answer, the right code. Okay. Any questions? Is that clear? Okay. I put the truth table up there. So, and that allows us to use the parity check. Sorry, this is just to remind me to put the truth table or derive the truth table. So, so now that we have the truth table and we know how to do error correction, and that's the beauty of it, I never have to know what the actual bit is. I just need to know which one I flip, which bit to flip to get me the right answer. Okay, so this is an automatically error correcting code, but how many bits of error can it correct? Okay, once again, it's only a 1-bit flip, right? Because if more than 1 bit flips, then this error correcting code doesn't work. Okay. Okay. So yeah, so that's what I wanted to say here. So, but of course, now I have more bits, right? Instead of having, if I wanted to transmit a 0, right? Then now I'm sending 3 zeros. Okay. So yes, my probability of my error correction code can correct the error, but the probability of errors increases. Right? So my probability of errors is now higher because I have 3 bits to transmit. Okay. So the code can only win if the probability of error is less than using no error correction, right? If I don't want to use error correction, then I need to have the probability so low that that this code is not important, for example, or the code will only win if the overall probability of this error is less than the probability of error when I don't use error correction. Okay. So if the probability of error bit flip is P, then what's the probability of 3 errors? I can have an error in bit A, all 3 bits, right? So there's a probability of error in the first most significant bit, there's a probability of error in the second most significant, and the probability of error in the third most significant. What's the probability of 3 errors? If I have a probability of 1 error being P. Yes, one of you, either one. PQ, very good, excellent. Sorry, PQ. And if the probability of error is P, then what's the probability of 3 errors? Sorry, not 3 errors, 2 errors. Yes, P squared. But that means that there were 2 errors, one in each of the, say, any one of the 2 bits, and the third bit did not flip, right? It had no error. So we need to multiply by the probability that the third bit does not have an error. So it's P squared times 1 minus P. This is like a coin toss. Okay, so in a coin toss with a coin that has a probability P to be heads or tails, to be heads, for example. Right? Usually it's half, right, when you toss a coin. But if you have a probability that the coin is not fair, and it has a probability P to give you heads, then if I want a string of, say, 2 heads and 1 tail, then that's P squared times 1 minus P. Does that make sense? Yeah. But of course, that T, the tail, can be in any one of 3 locations. Right? It could be HHT, HTH, THH, and then one, and similarly for all the other possibilities. So we need a factor of 3 in front. Right? So that's the probability that there's 2 errors in the code. Okay. In the string that I sent. Okay. So the overall probability of my error correction code, probability of error, is the sum of these 3P squared times 1 minus P plus PQ. Now, what's the probability of error if I don't use error correction? It's just P. Right? So I can only win with error correction if the sum of these 2 errors is less than the error of not using of not using error correction. Okay. And so the domain of this error correction advantage is just very straightforwardly, if I call this 1. Sorry, I just can't get with this thing. And I have to basically write out 3P squared times 1 minus P plus P cubed is lesser than P, right? That's the domain of my error correction advantage. I am not going to even attempt it with my silly little pointer here, but hopefully it becomes clear, right? It's just adding these 2 errors has to be less than this error, or equivalently, this plus this minus this has to be lesser than 0. Okay. And so you can easily look, you can use, any software package you like, Mathematica is my favorite one for symbolic stuff to simply solve the inequality, 3p squared and 1 minus p plus p cubed less than p. You can use it, you can just use Mathematica to solve it, or you can use Sage Math, which is a Python package, which does symbolic mathematical computations, or you can just graph it, which is what I like to do. Okay, so I just graph 3p squared times 1 minus p plus p cubed minus p, and I just look at where in this place it's going to be less than 0, it's p lesser than 0.5 half. Okay, so as long as the probability of error is less than half, this will win. This error correction scheme will win. Okay. And fortunately, it turns out that with semiconductor technology at the level that it's at right now, this probability of error is minuscule. I think it's like a part in billion or something like that at this point. So we don't even bother with error correction most of the time with modern digital computers, or they may have some very basic kinds of error correction. Maybe not even this. Okay. Now that I've introduced. Any questions about error correction schemes? Why I introduce it here is because these same ideas, like the things I did with that Toffoli gates and also with this error correction, will return to us when we do quantum computation. So it's helpful to see the classical analog, and then when we do quantum, hopefully you'll recognize the same types of ideas, except we have to modify them to take into account the weirdness of quantum mechanics. Yeah. Okay, so if there are no more questions here. I now want to introduce the concept of a Turing machine. Okay. So there's a powerful quote by one of the famous people in computer science who wrote a famous book about algorithms. And his comment, his statement is, algorithms are concepts that have existence apart from any programming language. Okay, so that's an interesting idea, a concept. It's like a mathematical thing, right? I mean, people have debated for very long whether mathematical objects have a reality or an existence apart from, what we use to visualize them or to write them down. Anyway, it's an old argument about the reality of mathematical objects. But anyway, so the model of computation, I mean, I know it's very basic computation. We haven't really produced anything that looks like a computer in any of the stuff that I showed you. I just showed you like digital logic gates, and I said, extrapolate this to infinity, and you'll get our modern classical computers, right? I mean, that's what is basically in our modern classical computers. It's just a whole bunch of these logic gates. In every different way that you can imagine. But beyond the circuit model, this is not the only model that one can imagine for computation. Okay. And the most famous and the useful one, because of very powerful theorems that has been introduced, is by Turing, which is called the Turing machine. Okay. Turing, as you may or may not know, Alan Turing was a famous mathematician who was responsible to a large extent, for example, in laying obviously the foundations for mathematics, for computer science, but also he was famous for being one of the people who figured out how to crack the code for the Enigma machines that the Germans were using during World War II. And so he built machines that allowed the British to crack the cipher for the Enigma machine, and thereby decode all those messages and allowed us to, win the war, essentially, or win the war against the Nazis. Coming back to there's a famous movie, you might have seen it, called The Imitation Game. I don't know if anybody has seen it. Yeah, it's a nice movie, I think. Anyway. So it has 4 parts, the Turing machine, which are called the tape, the head, and the register, which also goes by the name of finite state control, and the program. And so I'll just show you the sort of a drawing, which makes it hopefully more clear. Okay. So we have an infinite tape, basically. You just think of like a tape, a long string with like cells, and on each cell, each box in this tape, you can have several symbols, an alphabet for your Turing machine that the Turing machine recognizes. Okay, so the alphabet, I'll introduce it in a minute, but it's very straightforward. It has this right triangle symbol, which is like a play symbol, and then 0 or 1, right? And blank. Okay, so blank is also an allowable alphabet, symbol in the alphabet. There's also a head of the machine. So this is very like how in the old days, how the computers were constructed. So you can see that his model of a computer belongs in that same idea. Like he had no way to like imagine electronic circuits, and he knew about electronic circuits, but I'm just saying, I think, he restricted himself to something like this. Is very, like exactly like an old machine, like a tape playing machine. And so the head of this Turing machine moves one by one sequentially through the tape and executes a line of the program which depends on the internal state of the Turing machine. Okay, the state of the Turing machine can be any one. Oh, sorry, let me just add that. So the states of the Turing machine can be anything between, call it Q1 up to Qm, where M is the number of states. But there's one special state, Qs, which is called the start state of the Turing machine, and there's one special state, the halt state of the Turing machine, which is QH. Okay, so those are two special states that have to be there, okay, in the Turing machine. And a program is just a set of lines which look like this. Okay, so in this case, what the line says is QS. This is the starting point. The state of the machine is QS. When it is QS, then the head is reading, and if it reads a symbol right triangle, then it should write the symbol right triangle or play in this case, whatever you want to call that, and then it should move to the right by one cell, and then change its state to Q. And that's one line of the program. Okay. So in this, effectively what it does is it just keeps the state the same, which is this play, and then moves one cell over and changes its state to Q1. Okay. So now when it searches through this set of instructions, it'll look for the first line that matches Q1 and the input that is over here, and then it'll execute the rest of the program. Well, let's do an example. Okay, but is that clear so far? And the symbols I already introduced, 0, 1, blank, and the play. Okay, so here's a program for a Turing machine to add 1 to any number. Okay, and we'll work through this program, but I just put it up over here. Okay, so again, it's just like that. QS, play, move 1, increment your state to Q1. Okay, let's go through it. If I keep that up there, I'm still distracting. Rewrite. So for this, I'm going to use here's the tape. And the tape is loaded, of course, with our favorite symbol, play, and QS, which is the starting state of the Turing machine. Okay, and the input to the Turing machine is over here. Okay, this is the input to the Turing machine. And then this is the last one is a blank. Okay, the blank, and then you can think of it as having an infinite set of blanks after that. Okay. So and the code, the program for the Turing machine is QS I leave this blank. I could write B if you like, blank, but just blank. And so the states, the movement of the tape head can be right or just stay. Stay is just denoted by a dot. Okay. Let's work through this Turing machine and see how this program and see how it increments our 1011 by 1. Okay. All right. So the first step, it sees the play, right? It moves over one step to the right, remains in the state Q1. Okay. But now it sees now it searches through the set of instructions. If its state is Q1 and the input is 1, it should write 1 again, that is, write the bit back to the tape and move to the right. It will move to the right here. After the first line of the code, you have a 1 and it remains over, it is now over here in the state Q1, right? Is that clear to everyone? So first, sorry, I kind of skipped, but yeah, here is now 1. Now after the second line of the program, it is now moved over one set. Now it's searching in the code for when it has a state Q1 and the input is 0, it writes back a 0. Again, same idea, it writes back the same number and moves to the right. The right. So the head is over there, the state is again Q1. Does it again? Q1, right? And at the end, after this one, this is the first moment where we see, when we see Q1, we see a blank. We write the blank, but now we move the head to the left. So now after that step, let me sort of draw the final step over here. After we see the blank over here, the head has moved back over here, right? It wrote a blank here, so preserved that state, but now its state is Q2. Is that clear to everyone? Okay. And the first one, 0. None of this has changed. Okay. Now that it is Q2, what it says is if I see a 1 here, I need to write a 0. So after this step, I have incremented. I've changed this cell to 0, and I move to the left, and I'm in state Q2 now. Right? Then again, I see a 1, right? So I must increment that 0 or write a 0 on it. Okay. And I must be over here now in the state Q2. Finally, when it sees a 0, okay, it writes a 1 and stops. I guess it's, you call it image. Okay. So it has stopped the program. Okay. And so this is basically the operation of the Turing machine. You can verify for yourself. This is indeed 1011 added 1 gives me 1100. Okay. So that is how a Turing machine can work to, and so the idea is that every Turing machine is specified both by its program and also by the input. So this Turing machine here would have a certain number. I could assign a number to it, okay, by some method that I won't get into, but that's what Turing did. He could have figured out a way to assign to every Turing machine some kind of number, okay, and enumerate. Any questions on this? Oh, sorry, before I. Any questions about that? I can show it again if anybody had a, yeah.
I just want to ask a clarifying question real quick. So
Yeah.
The script that left written on the right.
Yeah.
is like the instructions need, that is specific to this Turing machine.
Yes, that's correct. So there's a Turing machine for every single operation. It's not a high level programming language. You can think of it like assembly language, right? If now that, sure, some of you might have done some assembly language programming. So, yeah, so as I said, and of course, you don't need to restrict yourself to the simple basic Turing machine that we have. You can imagine a Turing machine with multiple tapes, two-way tapes, so the tape can move not just to the right, but also to the left, maybe. You could have like two-dimensional tape, right? So your Turing machine operates in 2 dimensions or higher dimensions. So there are infinite variants of the basic Turing machine, but what again, a powerful theorem, when I say we, I mean computer scientists have shown that they are all equivalent to the basic Turing machine that was first, this one that we just talked about. Okay. And what I mean by equivalent, what do we mean? It just means that the basic Turing machine can simulate all these other types of Turing machine with only a little bit extra overhead. Okay. By little bit, we'll define that more carefully in a minute, but it basically means it's somewhat a finite amount of time. Okay, then we come to the universal Turing machine. So I just talked to you about, every Turing machine, we can define a number. Turing called it the Turing number. I mean, not Turing, but Turing gave it a number and people now call it the Turing number, which defines the basic components of our TM, or Turing machine. So just, you take the tape, the program and the tape contents and you somehow do a hash function on it to encode that as some number, which we call the Turing number, okay? And there exists a universal Turing machine that can simulate all the other Turing machines. So if I give you the Turing number T and the input X, the output of this universal Turing machine will be T of X. So therefore, we just need one machine, which is the universal Turing machine that will encode all the other machines, okay? So anything that we say about computations now can be put into the language of what is it that a universal Turing machine can do. Okay, and why is that? We'll just talk about that in a minute. So what do we mean by computability? Okay, this is the big question that computer scientists were struggling with, still struggle with to this day, but certainly back in the 1940s, 50s, as these things were starting to become more and more emergent, they really worried about this. Okay, what is it that we mean by computability? Okay, and Church, Alonzo Church, he was another famous computer scientist, and Turing put forward this thesis. They said that the class of functions computable by a universal Turing machine corresponds exactly to the class of functions which we would regard as being computable by any algorithm. Okay, so the idea that what is an algorithm? Well, I kind of defined an algorithm for you here for the Turing machine, but you do algorithms every day, right? When you wake up, how do I brush my teeth? Okay, I have this algorithm. I go up, I take the toothbrush, I take the toothpaste, I squeeze. So that's an algorithm, right? And so on and so forth. So almost everything in life we think might be written down as some kind of an algorithm, some steps. So that's our intuitive definition of what an algorithm is. And then, in computer science or in mathematical functions, we can also think about, I have a function and here's an algorithm to compute the function on all its inputs, for example, right? So this is another example of an algorithm. So the Church-Turing thesis, that the role of functions that are, or the class of functions that we can regard as computable is all computable by a universal Turing machine. So far, we have found no counterexamples to this particular hypothesis. But it's still unproven. I don't know that there can ever be a proof of this particular hypothesis, but this is the Church-Turing thesis, but it's still unproven. And tomorrow somebody may find a counterexample in nature, or we can design one that violates this. That is something that would not be computable on a Turing machine, but which we could say is definitely an algorithm, right? By the way, I should mention that the Church-Turing thesis did not say that the computation would take a finite amount of time. Okay, it's just that it must be computable on a Turing machine. And we have also not said that every function is computable. Okay. But I also want to finally emphasize quantum computers obey the Church-Turing thesis. Okay. They don't violate this thesis. Okay. They are still within the class of computers that a universal Turing machine could simulate. So what is it then that quantum computers give us? We'll come to that in a minute. Any questions about this? Maybe as things go along, this will become more clear. Okay. So the most famous example of a problem that cannot be computed is the so-called halting problem. Okay. And this is a problem, the statement of this problem is there exists an algorithm to determine if a computer program, that is a universal Turing machine, will halt. Okay. Or if it will run forever. That's the infinite loop. Okay. So either just that one simple question, if I give you a Turing machine with some input, a universal Turing machine with some input, with the Turing number and the input, can you find out if this program will actually halt and doesn't just run forever? Turns out this is an undecidable problem. This is in those class of problems which are undecidable. Okay. Turing proved that there is no such algorithm. Okay. This is a fantastic, sort of achievement, I think. Going back to this, we'll come back to this in a minute. So the proof is by contradiction. Okay. So there are two programs which one is called H and one is called Z. Okay. And they both take as an input another program P. Right. And as we said, programs, etc., can be thought of as some number. So you think of it as a function that computes some output, and that can then be computed on a Turing machine. Okay. So program H is the one we are looking for. It's the one that says if P halts, it will return a true, and false if it runs forever. Okay, if it does not halt. Program Z takes an input P and returns forever, runs forever. It runs forever if H of P is true. That is, if H of P, meaning if P halts, right, then H of P is true, then this program Z runs forever. Okay. And similarly, it will halt otherwise. Okay. So this is the very basic construction. Is that clear to everyone of this proof? Right. So now the proof by contradiction will come along. By the way, I'm just questioning. How many of you have heard of this halting problem? Oh, ever. You all know the proof there? No. Oh, that's good. I wasn't sure if I'm just going over something that's very well known to all of you already. Okay. So I mean, in some sense, I could so H of P, I could write this in pseudocode if I want, right? So F H of P. Okay. Sort of Pythonish. If P halts, return true. Right? Else return false. Can everybody see this, by the way? Am I writing too small again? Back there, you can see it? Okay. I sometimes end up squeezing my things down as I go down the board, so please let me know if that happens. And Z of P, if H of P true. Sorry, this is not Pythonish anymore. I can just say if H of P in Python, right? So if H of P, right, is true, is Python, then run forever. So just say while true. Okay. Pass something. Leave, whatever. Else return. Okay. Right? Hopefully that makes sense. Okay, so let's say P1 parts. Let's say somebody already told you P1 parts. Okay. Then H of P1 will be true, right? Then Z of P1 will be what will it do? Yes. Infinite loop. So Z of P1 does not harden, right? Okay. P2, somebody else gives you P2, which does not harden. Which implies Z of P2 now comes the magic, right? Consider the input Z of Z, graded recursion. Right? I give Z back to itself. What's going to happen? Okay, let's check all the possibilities, right? Okay, let's go into the loop. Okay. So if H of Z is true, right? Which means Z hards, right? H of Z is true, means Z hards. What will Z actually do? Loops forever. And the other converse is hopefully obvious, right? So if H of Z is false, that means it's supposed to loop forever. Well, Z will return and stop running. So it will harden. So that's the contradiction. Okay. So that means we cannot have this program that exists like this. Okay. Okay. So that was the famous proof of Turing, and you can see how beautiful it is. With just this beautiful construction, he was able to. And the reason that these things come about is because, of course, of the powerful idea of the Turing machine, that there are machines that can take some tapes and run these algorithms and programs. And he made it, of course, much more rigorous than what I'm doing here. The fact that I wrote a pseudocode and said that can have a Turing machine, a Turing number, well, that has to be something you have to establish. Because I might write whatever I want on the board. It's not clear that there exists a Turing machine that will execute that program, right? And so the fact that he had to show all those steps also, of course, that each of these corresponds to some kind of Turing machine. And then you can take this Turing machine and give it its own input, so to speak, and see what happens. Okay, so that's the sort of the rigorous parts of the proof that I'm skipping here. Okay, I have a few more minutes, so let me just talk about computational problems in general. Oh, sorry. So we have talked a lot about what is a Turing machine and so on, and we are going to restrict our attention in these Turing machines to decision problems. It turns out that a huge class of computational problems can be classified as decision problems, i.e., those are problems to which you get a yes or no answer. I'll give you some examples in a minute. Okay. The second big question that we have with computational problems is how can we design algorithms to solve a given computational problem? That's beyond the scope of this class, because of course, for that, you need to go take algorithms class in computer science department. Okay. But I will talk about quantum algorithms later on. Okay. And the last sort of question you could ask yourself when it comes to analyzing computational resources is, what are the minimal resources required to solve these computation problems? And to do that, we'll introduce the idea of something called asymptotic notation. Okay. I'll introduce that on this slide. So we quantify. So I'm talking about the last question first, and then I'll come to what I mean by decision problems and the classes of decision problems at the end. Okay. So when we want to quantify computational resources, we just want to know the essential behavior of the algorithm. We don't care in this case about factors of 5 or 10 or even 100. Or nor do we care about constant overheads, even if the constant overhead is like 1,000 or something like that. Okay. So that was introduced in computer science by the notation big O. Okay, so big O of n sets an upper bound on the behavior of the algorithm. So let's introduce what big O of n means in a second here, which is I take two functions on the inputs n. Okay, f of n and g of n. They're functions of non-negative integers n. Think of n as the number of bits in your number that you're trying to figure out something about, or the number of bits or words or whatever in your document that you're trying to process. Whatever it is that you're trying to do, it can be written down in some finite number of bits. So we say f of n is big O g of n. If there are constants c and n naught such that for all values of n greater than n naught, f of n is lesser than or equal to cg of n. Okay, it looks confusing, but the basic idea is beyond some value of n, okay, cg of or g of n is the upper bound for f of n. Okay, times some constant factor, which I don't care about. Okay. So the big O notation captures sort of worst case behavior for the algorithm. Okay. As n gets bigger and bigger, essentially you can think of this as it'll approach these values of this g of n. Okay. There's one other notation, which is big omega notation, which sets lower bounds on the behavior of the algorithm. So again, it's the same idea. I have f of n and g of n functions on the non-negative integers. And we say f of n is omega g of n. Again, if there are constants c and n, such that for all values of n greater than n naught, f of n is the upper bound for cg of n. Okay. So at worst, it'll always be faster than this situation, than this g of n. And we can also use something called big theta notation. I won't be about that. It means that f of n and g of n are the same in the asymptotic limit. So examples, okay. So here's a problem given n men and women who have ranked the other group in order of preference. Pair the couples up so that nobody would rather be with someone else than with their spouse. This algorithm solves in O of n squared time. Okay? Big O of n squared. Okay. And the idea is, as you can imagine, that as the number n goes larger and larger, that n squared will always form an upper bound for the running time of this algorithm. Okay. With primality decision problem, this is another decision problem. That is that deciding if I give you a number, is it prime or not? That is solved in order or big O n of n to the power 6. Okay. Maximizing a linear function constrained by linear inequalities. This is the famous linear programming problems that if you take some course in operations research, or maybe you've even seen it in some math classes, that is O n cubed, okay, big O n cubed. Okay, so now I can tell you what a complexity class is. An algorithm is called efficient if it takes polynomial time or less. That is, if the runtime is big O n to the power k. Okay. So anything which looks like n, even if it is say log n is obviously even sublinear, right? As n becomes larger. So that is also efficient. Okay. Obviously, a constant runtime is very efficient. Okay. No matter the size of n. N log n is also efficient. Okay. When I say efficient, it has a very specific meaning in computational resources. It has to run in polynomial time. Okay. And it's inefficient if it takes more than polynomial, which is generally given the name super polynomial time. I'm out of time. So just this last slide. So that includes things like exponential time, so 2 to the power n, or e to the power n divided by, say, 1000 even, doesn't matter. Includes sub-exponential time, 2 to the power n to the fraction 1/3. Or for many values of time, you can see, for example, if I said k was 1000, n to the 1000 is a very large number, okay? And e to the power of n to the n divided by 1000 may be a very small number. So it isn't always true that this is always more efficient, but we call them more efficient. We call it efficient. And the reason is, of course, we're always looking at this asymptotically for very large values of n. That's what we really care about, okay? And it doesn't mean that for small values of n, this may not outperform that one. Okay, it can. It will outperform that one for such examples. Okay, the next class we'll talk about complexity classes.